So we've learned a little bit about triple integrals, namely how to calculate a simple triple integral, and that when you're taking a triple integral, the limits of integration will represent a solid in XYZ space. And then we drew several graphs of what that would look like, what that solid would look like, and which direction you'd be going, and where your region would be in what plane. So if X and Y are your region for your dA, then that would be XY plane. But if you're in respect to Y first, then X and Z would be your region, which is on the XZ plane. And then if your region, if you integrate with respect to X first, then dA, the area, would be in the YZ plane, which is the hardest to see, but it's kind of like you're shining a light from where you're looking at on the screen back towards the YZ plane back here on the back wall. All right, now what is it that the triple integral is representing? Well, if we're taking a triple integral of 1 with respect to volume, then what we're finding is the volume. Much like when we took the double integral of 1 with respect to A, we were finding the area. When you take the triple integral of 1 with respect to V, you're finding the volume. Essentially, you're allowing your function f of x, y, z to be equal to 1, and that means that the triple integral will find the volume. Now, what if it's not constant? What if it's not 1? Then what are you finding? Well, you're finding delta. This is the Greek letter delta, which represents the density of the solid. And if we integrate that density function, so the function itself is the density, and then the triple integral will represent the mass of that object. So the object that is defined by the limits of integration d, then your function delta represents density, and then your triple integral will find the mass of that object. All right, so set up but do not evaluate 3 different triple integrals that represent the volume of the tetrahedron in the first octant, bounded by the coordinate planes and the plane 6x plus 4y plus 3z equals 12. For each variable once, or use each variable once as the first variable of integration. Evaluate one of these to find the volume. Right, so it's saying do not evaluate, and it's saying evaluate one of these because hypothetically speaking, this should always come out the same. It shouldn't matter which way we go, right? So triple integrals, it won't matter what direction we go as long as we do it correctly. So let's see which way I begin first. So I first begin in the xy plane. Pretty standard beginning. So the xy plane, what I did was I solved this equation right here for z. So if this is my plane, 6x plus 4y plus 3z equals 12, then if I get z by itself, right, subtract the other 2 terms from 12 and then divide everything by 3. Right, so that's the xy plane. And if you'd like to see it in Maple, if you don't believe me how it looks, this is really what it looks like. So I used a plot 3D function, and there's my object. Right, so I have a plane, it's getting cut across by the xy z-axis. There's the shadow it's casting, the region it's casting down onto the xy plane down below. All right, so if that's the case, and I want to build this volume integral. So I want to start off with figuring out the shadow down below because that shadow will help me find my limits of integration. So I think, oops, sorry, that's going to keep happening. The triangle shape that we can see on Maple is happening down below this. So if I set z equal to 0, because of course on that xy plane z is equal to 0, so then 6x plus 4y would be equal to 12 because there'd be no z term. If you go back up here to the equation of the plane, if you put z equals 0 in there, it'll all go away and you'll be left with 6x plus 4y. And of course we all know how to solve that for the equation of a line, right? Subtracting the 6x, dividing by 4, and simplifying a little bit, you'll get y equals negative 3 halves x plus 3. So then I draw that. That's a diagonal line right here. And then I think x is going to go from 0 to 2 because that's the x-intercept. Y is going to go from 0, not to 3, 3 is the top. It's going to go from 0 to that line. So I'm doing a vertical bar on this region. Okay, so when I want to write this volume function, I want to say, it's going to keep happening, but I want to say take the 1 first of all because I'm finding volume. Right? Since I'm finding volume, I'm going to use 1. Right, if I'm trying to find mass, I would use a density function, but I didn't have one given to me. So I'm going to use 1, And then I'm going to do this with respect to z first because I'm doing this in the xy plane, right? So I'm going from xy plane up to that surface. So dz is first, and z goes from 0, the xy plane, up to where that triangle plane hits it. And that would be 12 minus 6x, or excuse me, minus 4y minus 6x divided by 3. So I'm going from this plane down here. There's that triangle that I just played with. See, it hits at 2 there and 3 there. 2 for the x, 3 for the y. And then I'm having it cast up onto that z. In this case, it's a plane. Of course, it could be a function, but this one is not. Now, the y limits are going to go from 0 to negative 3 halves x plus 3, because for my region, which is a triangle, the y changes from 0 at the bottom of the rectangular bar across that triangle all the way up to that line. And then the last will be the constants. Just like with double integrals, the first two integrals, the pink one here and the blue one here, will have functions. I mean, not always. You can have constants for them, but that's kind of boring because that makes a cube. So you'll usually have functions on the first one especially, the first two often, but the last integral has to be constants, has to be, just like it was for double integrals. So the last integral will be with respect to x. Now if I type this into Maple, I'm going to get an answer, which, here, let me show it to you real quick. Oh, finding the integral right here. So if I did this integral, the function is 1. Z is from 0 to what I just said, right, that function. Y is from 0 to negative 3 halves x plus 3, and x is from 0 to 2. So I typed that all into my integral feature, and I got 4. So this was way number 1, dz dy dx. Okay, so way number 2, let's see here. I'm going back into the xz plane, so I'm kind of putting it to that side wall. So I solved the function for y then, instead of z like I did up here. So when I solve the function for y, I get this, right? If y is equal to 0, then 6x plus 3z is equal to 12. Right? So again, going back up to this plane function right here. So if you put 0 in for y, because that's your first integration is going to be with respect to y, then you'll have 0 there. So you'll have 6x plus 3z equals 12, which is right here. And then you solve that for z, you'll have z equals negative 2x plus 4. So now I'm going to draw the triangle in the xz plane right here. So the x is going to go from 0 to 2 again, but the z is going to go from 0 to that function, negative 2x plus 4, right there. And if I look at the figure in Maple so you can see, so if you're looking at the xz plane, you're looking at that triangle right there. It's kind of hard to see, but this back wall. So you're saying the x goes from 0 to 2, but the z goes from 0 to this line, wherever it intersects it, right? Okay, so that's the next one. So the integral is going to go from, it's going to be of 1. 1 is my function. I'm going to do the y parts first, which are from 0 to the 12 minus 6x minus 3z over 4y function, right there. 4 function, right? That is my y equals function, not 4y. And then the z is going to go from 0 to that line, negative 2x plus 4, and yet again my x is going to go from 0 to 2. All right, last one would be, well, let's see, we've done the xy plane and the xz plane. So that leaves us with the yz plane. So I have to take my function and solve it for x. All right, so when I solve it for x, let me go back up here. That would be subtracting the 4y and the 3z to the other side, and then dividing everything by 6. So that's what we do, right? So right here, x is equal to negative 3z minus 4y over 6. So I'm kind of pushing the picture into the back wall of the the yz plane. All right, now the shadow it casts onto that yz plane would be what would happen when x is equal to 0, because you're in the yz plane. So I'm going to put 0 into my original plane function, 4y plus 3z equals 12, and solve that for z. And therefore my z goes from 0 to that function, negative 4/3 y plus 4. And I don't have z or x in this case, I'm going to have to pick a different constant, so I took y. Y goes from 0 to 3. And if you're wondering, could you have solved this blue part here with x equal to 0? Could you have solved that for y and then reverse these? Absolutely could. It's just whatever is convenient or easy for you to think about. All right, so yet again, I'm going to take the integral of 1. I'm going to do the x part first, so I put in that x function, then the z part next, and then the y part. And according to me, it should work out to be the exact same every which way, and it does. So when you look at Maple, Maple's showing us, that it is exactly the same. It's 4 when I do it with respect to z first, then y, then x. It's 4 when I do y first, then z, then x. And it's 4 when I do x first, then z, then y. They all work out to be 4.